Chapter 13 covers the basic concepts and applications of chemical equilibrium. I will divide the lecture for this chapter into several parts. Let's look at an example that shows how the concentrations of reactants and products change with time for the reaction of sulfur dioxide gas with oxygen gas to form sulfur trioxide gas. We can write an equilibrium constant expression for this reaction. Again, we would write the concentrations of the products raised to the power of their coefficient in the balanced chemical equation, divided by the concentrations of each of the reactants, also raised to the powers of their coefficients in the balanced chemical equation. In this case, again, when our value is K, we're specifying that the system is at equilibrium, and these are the equilibrium concentrations. We can also write an expression for Q, the reaction quotient, for this system. Notice that it's the ratio of the same concentrations raised to the same power, but we just use a subscript T to indicate that these are not necessarily equilibrium concentrations. In the first case, the diagram on the left, we're going to start with only reactants present. At this point, the value of QC would be equal to 0 because the concentration of sulfur trioxide, the product, which appears in the numerator of the ratio, is 0. As time goes on, reactants are converted to products, and the value of QC will increase until it is equal to Kc, and the reaction is at equilibrium. The second example on the right starts with only products. Here, the value of QC would be infinity. By plugging 0 in for the reactant concentrations, since those are in the denominator of the fraction, would give us a value of infinity for Q. This means that Q must be greater than Kc, and the reaction is going to have to shift or proceed in the reverse direction to reach equilibrium. Reactions will always proceed in a direction that takes them towards the equilibrium position. This next slide summarizes some important ideas about QC and Kc. Again, we'll start with our generic chemical reaction of A plus B goes to C plus D with the corresponding coefficients. We can write expressions for the value of Q and also for the value of K. What's important about the reaction quotient QC? First of all, the value of QC depends on the initial conditions and on how much time has elapsed. When QC is greater than Kc, that means there is too much products present and the reaction has to proceed in the reverse direction to reach equilibrium. On the other hand, if the value of QC is less than the value of Kc, there's too little products and the reaction will have to proceed in the forward direction to reach equilibrium. The value of Kc, on the other hand, is a constant at a given temperature for a given reaction. What does the value of K tell us about the reaction? Well, when the value of K is much greater than 1, that means that this ratio has a larger amount of products compared to the amount of reactants. So there are mostly products at equilibrium, and we say that the reaction is product favored. On the other hand, if K is much less than 1, that means that there are mostly reactants at equilibrium, and the reaction is said to be reactant favored. So what do the values of Q and K tell us? The value of K tells us what the system will look like when the system is at equilibrium. In other words, will there be more reactants or more products at equilibrium? The value of Q is really only important in comparison to the value of K. The value of Q will tell us in which direction the reaction must shift in order to reach equilibrium. Here's another example for a simple reaction of A going to 2B. What do the concentrations versus time look like for a system in which the value of K is much larger than 1? If we start with only reactants and no products, here's our initial conditions, and we watch this reaction as we go towards time. In the beginning, we see that the system is not at equilibrium because the value of Q is 0. Since Q is less than K, the reaction must proceed in the forward direction. This means that the amount of A will decrease over time and the amount of B will increase over time. At some point in time, the amount or concentrations of the reactants and products will no longer change, and we say that we have reached equilibrium. In this particular example, there are more products than reactants at equilibrium because the value of K was much larger than 1. Sticking with the same reaction, A goes to 2B, and sticking with the same equilibrium constant that has a value of greater than 1, what do the concentrations versus time graphs look like if we start with products and not reactants? Again, we're showing the product concentration in red and the reactant concentration in blue. So our initial condition is to start with products only. If we were to evaluate Q at this point, we would find that the system is not at equilibrium because Q does not equal K. In fact, Q will be equal to infinity because the reactant concentration is 0. Since Q is greater than K, the reaction must proceed in the reverse direction in order to reach equilibrium. This means that the amount of reactant will increase over time and the amount of product will decrease over time. At equilibrium, we'll still have the situation where there is more products than reactants. In this video, we looked at some basic concepts of chemical equilibrium and equilibrium constants. The next video continues by looking at how to write equilibrium constant expressions for reactions that occur in the gas phase or reactions that involve pure liquids or pure solids. We'll also show how to combine equilibrium constant expressions.